the way that I actually try to describe to you is in a corrosion, it's actually looks like a dry cell. So when you have something that's over here, you start to realize that a battery, right? If you don't use it, right, you'll never spoil. But the moment you start to connect a wire, the battery gets drained off, and then it actually will be depleted. Actually, what really happens is there is an oxidation process and a reduction process, and during the process, something happens. So I want to use a simple idea that one of them, okay, maybe this one will be, let's say I call it, let's say T, let's say N plus NE to T. So over here, in a very simplistic term, the way I've written here, if you look at the oxidation number, this is a 0 and go to a plus, right? This is an oxidation. So this is a reduction. So plus to a 0. So this is a reduction. So in any kind of a corrosion process, they have to have two of this happening. So one will be the anode and the other the cathode. So one will want to give away the electrons, and one will want to consume the electrons, and the electrolyte will actually complete the circuit. And because of this, there is an electron flow. And this electron flow is basically what you have in your battery, the dry cell. And depending on the cathode and anode, right, you can have, for example, the different voltages or the electro EMF, electromotive force. Okay, so those are based on the pairing. So this is important to know that this is actually a corrosion in a very general sense. It's an electrochemical process. So this one, trying to go into the picture, right, is really over here. So over here, the zinc is being oxidized. So zinc becomes Zn2 plus, and then the electrons start to flow. The other one will want to consume the electrons, and over here. Now the question becomes very strange, right? Both of them will be likely to have oxidation or reduction. So which one is the most preferential? All right. So if you start to look at the idea of corrosion, right, a material can both give or take electrons, right? And what determines those? And the one that actually determines those, I think, if in the more simplistic term, I would like actually you to refer to this whole idea of the electronegativity. So electronegativity is a very simple idea that looks at any atoms. What is the demand for electrons? So something that is very high, basically this has a scale of 0.7 to 4. Fluorine has a 4.0. So this one amongst all, right, is the one who is hungriest for electrons. All right, a smaller number is the one that's really want to give away electrons. All right, so you start to pair two of these things up, right? You start to realize that one want to give and one want to take. Okay, so if one of the electrode is as such, then there will be a driving force. And typically, when we talk about materials, right, we could well be pairing, for example, sodium and let's say magnesium. So in this particular picture, all right, you know that magnesium is also one that want to give, sodium also want to give, but in this case, when you pair them up together, right, sodium will want to give up more than the other one. So there is a certain pecking order. All right, all this actually boils down to the very simple idea of the electronic structure. So if you go back to a little bit on the basic chemistry, this is what it means. But when we go down to the materials, when we try to actually plot the EMF series, basically we do have a few kind of guiding principle. We create a standard EMF. Basically tells you if these are all the corrosion. Over here, these are all the reduction process. Okay? All the reduction process. We write in a reduction manner. So over here, the voltage is on the higher side, more positive, right, will be the one that is increasingly inert. So it doesn't, you will not actually create a lot of a problem. Right? If you start to look at here, gold is, if you go and check the electronegativity table, it's one of those that is, not as low a number. Okay, basically it doesn't. And then you go to potassium, right? It's your group 1. So when you start to do this, right, when you do a coupling, so for example, chromium and magnesium, right, between the two, if I put one chromium plate and a magnesium plate, all at standard condition, I will expect magnesium to corrode chromium to under reduction. Okay, but if you try to put something above nickel and chromium in this case will be the one corroding. So depending on the parent, all right, who is the counterparty, which one will want the electrons more. So that's the whole basis of this EMF series. Okay, one want to give and one want to consume. The one that actually give, you have to become an ion in the liquid, and in a simpler sense, right? Yeah, piece of metal, okay, which is a solid, want to dissolve in a liquid, means corroded. Okay, and the other side will be electro depositing. So depending on which end. So the corrosion will be one that actually shed material. The other one you can do plating. So you want to plate gold, or you want to plate nickel, electroplating, then you know the other side what is on the counterparty. Okay. So this is in the gist, in the whole idea of this corrosion. And then for this to work, if you try to look at and try to actually understand all the corrosion, even for example a single piece of material, right? So if I have a zinc, I throw it inside there, then a lot of the question mark will be, I only have zinc, I don't have another material. How come corrosion still takes place? So I have a piece of steel, right? It's still corrode. What really happens? Basically, any kind of chemical inhomogeneity, right, within the steel, or for example, in this case, a zinc, one side could act as an anode, the other one as a cathode. So one side will give, and the other side will actually become the reduction process. And then because this is a piece of metal, you have the conduction path, where electrons is transferred from one location to another. Locally, one side will be actually corroding. So this is the gist of all corrosion process. All right. So having the this mindset about the theoretical underpinning, right? Then when we go to corrosion process, then we start to realize that there are always 4 necessary conditions. Okay, you will have an anode. All right. So for anything to go, you must have an anode. All right. You must have a cathode. You must have an electrical connection. All right. And there must be liquid electrolyte. And this one will allow the ions to move to complete the ionic channel to complete the electric circuit. If this is a non-conducting, right, this one will not flow. So electrons will flow in this way. So anode is the one that's being corroded. Okay. Oh, okay, sorry.
So actually, in the sense that anything can be a battery,
Yes. If you use 2 different metals, it's a battery.
as long as dissimilar, right?
Yeah. So as long as you use a dissimilar metal, it can be a battery. For those of you who actually watch some of the TV videos for school, right? Sometimes they use 2 different metal, copper and a zinc, and then they put inside, for example, lemon, and then they try to light up a bulb or something.
Oh, the lemon is the electrolyte.
Yes. So it actually creates the current flow, because inside that lemon is actually acidic. So there's a flow electrolyte. Because if there's no flow, nothing will happen. So in the ionized water, right, means that there's no ion inside, it will not corrode. In salt water, a lot of ions inside, right, it will corrode very fast because of this simple reason. Okay, I just want to actually try to make it a simpler terms, right, corrosion of what you see every day, even your battery that you use, so they can relate to what we're trying to do here. So these are the 4 necessary conditions. So, which means, right, I need the 4 for anything to happen. Okay, if you start to look at a lot of the corrosion protection mechanism, right, you look at Boeing, Airbus, in future when you try to actually look at their lock and whatever, right, put sealant here and there. Actually, the whole idea is very simple. They are just trying to take away one of this to make it less. Cannot really. If you take out the wire, cannot corrode it. Just the battery will stay there for many years. Yeah, open circuit, there's no current flow. You take out the anode, right, cannot corrode. Yeah. Because actually you need all the components. The moment you actually open the circuit, there's no way electron flow. And that's the whole principle.
There
So
must
when I
be
have a building, right, I want to prevent rusting, like I paint. What am I trying to do? I'm actually trying to prevent the electrolyte from touching the metals. So if you try to actually start to look at all the corrosion protection methods, right? Actually, it all boils down to the key concept here. These four things. They are trying to make this thing less of an issue, all right, or make it less aggressive. Okay, to be honest, right, in some of the aircraft, right, for lack of a better word, right, bo pian, right, usually, if you want to choose metals, right, you want to choose that these two, right, not very far away from the EMF series or galvanic series. If they are very far apart, the driving force is very high, the tendency for corrosion will be very, very great. So you try to use, for engineering materials, something that's very close together. Does it make sense?
yes.
So it doesn't have that tendency. And then you can do further protection. So this is what you do.
Then the element table got give.
So this one is important because it gives you an idea what it does. And then when you come to here, all right, we have EMF series over here. This EMF series, all right, unfortunately, is only good for chemistry. Okay, if you look at here, all of them are all atoms. All right, and we know that for engineering materials, like we never like to use a pure material.
Yes.
So EMF series is not very good. So we also created another something, the same idea about here, but we created something called the galvanic series. So the galvanic series is the same idea. Something on top will be the one that is less likely to corrode. More on the bottom, the one that is more likely to corrode. So this one will oxidize more, this one will not oxidize as much. So anything below will corrode more than the top. So this one, in the galvanic series, we start to put in more real engineering material. So instead of iron, we put steel. We can put cast iron. So those are things that we use. And the reason why I told you we use alloy, right? Very simple idea, mechanically stronger. Because nobody will want to use iron by itself. People will use steel. Okay, so these are some of the reasons. Nickel or whatever. Okay, Monel, these are basically your super alloys. These are the whole reason why we use.
So what is passive, what is active?
Yes, this one I will share with you as part of the tutorial question. What is passive and what is active? Very good question. So stainless steel, actually the whole idea of stainless steel, right, is a common term that people use, right? This stainless steel in your mind will not rust. Okay, normal steel will rust. Okay, in the stainless steel, they put at least minimally 10 to 12% nickel, 13% of chromium. All right, when you look at the average, right, on the surface, they will have a chromium and basically nickel. And when they form the oxide, right, the oxide is highly protective. So, and the oxide, right, is protective to prevent the below layer from actually getting more oxidation. And one of the key thing about this particular oxide is it is adherent. Yeah, it sticks. So it sticks very well. So you try to scratch it, and it still stay there. And because of this, right, it has a natural protection layer. So when you have that, right, it means passive. But you can put in a stainless steel in a condition, right, the oxide actually disappear. Okay, you're always exposing new material underlying. So that's when it is active. So when the oxide is no longer there, it's an active state.
Oh, it's like when you cut those metal that is very reactive, then inside very shiny.
Yeah, after a while then become matte. Right?
Then become matte. That's
Okay.
the oxidation layer.
Yeah, for okay, a very simple idea for aluminium, right? Aluminium, if you cut a fresh piece, right, it's always very, very shiny. But the aluminium that you see, right, is actually very dull. It oxidized already. It has an aluminum oxide, and that's why it doesn't corrode as easily. So it's another one that is passive. And in fact, a lot of people will want to actually protect the aluminium by going through a process called anodizing. Have you ever heard of this word? Anodizing the aluminium. So they basically put the aluminium as an anode. No, you create an oxidation to force the oxide to form. And then, that's why in future you will never have
Well, but the oxide is cathodic, right? Or is it in a sense not reactive? Is cathodic or not reactive?
No, you put the aluminum as the anode. You make it oxidized. So you create more of an oxide layer on the aluminum so that in future it protects the aluminum from further attack. A pure aluminum. And in fact, for those people who actually are looking at the anodized thing, right? Because of thin film interference effect, some of the aluminum right will have a color, bluish tint, because those are the thin film interference effect based on optics. So again, these are small little tricks that people use to actually protect material. Okay. So over here, galvanic series differs from the EMF series from a very simple idea. The concept is similar, but galvanic series focus on engineering materials. Okay, EMF series is very good from the theory perspective, telling you from a chemistry perspective, individual atoms. It's good to lead you to the theory, but not great in terms of relating to a real world application. Okay, so engineers, right? We look at galvanic series more. But if in absence of galvanic series, we can fall back on EMF series to actually predict certain things, especially on the pure side. Okay, so basically that is all. And then there is something when you look at the EMF series and the rest, right? Especially for the EMF series, it's always done on the standard condition, which means 1 molar, 1 molar, all right, and then basically in 25 degrees Celsius. So these are the conditions. But in reality, you might be actually operating with a non-molar solution. It's not one. All right. How can you find the potential difference across? So then you have to use the Nernst equation over here. This is basically the standard value from the EMF, the EMF series table. R is your gas constant, temperature, Faraday constant 96500, and this is the concentration.
Let's go.
This one, if I test, you'll be given.
Oh, heng.
Okay? Because this one a bit long.
Tested lah. Your gift.
Huh?
Two formulas that appear in tutorial. Those are really need to memorize.
Yeah, pretty much. Actually, there's not a lot. I mean, I really restrict the scope so much already.
The stress and strain on.
Okay. Okay, can
Restrict my neck.
Okay, so and then the rest, right? The rest, I think I need you to know all the different types of corrosion. Alright, the different type of corrosion, how it happens, why it happens, and how do you actually prevent those things from happening. Okay? So all these are different kinds of corrosion.
My voice caught in high frequency.
And the reason why I need you to know is very simple. Somebody who has gone through a corrosion class, okay, no point just knowing the theory, right? Oh, I have these 4 things, right? I kill one, right? No corrosion. But when somebody, right, your staff, go and bring you this picture. What is this? Sorry, I don't know. I only know 4 things. Anode, cathode, So, being able to actually identify what it is, why it could have occurred, I think that's also a very important dimension in the corrosion class. Okay, over here in this course, right, there's 11 of them. I need you to actually appreciate what are the 11 differences and how,
11, let's go.
Okay, so next time when you go and you see, at least you can say something sensible. When you see 2 dissimilar metals, right, together, and then you say, oh, this one is uniform corrosion. Don't tell me that you attended my class. Okay. Can
next
but you understand where I'm coming from, right? Okay, so this one is something, because this is a skills that I think is application based. Okay, so I need you to know. Alright, and then when you go to the corrosion control, you start to look at here. Alright, this is a basic principle. We remove one of them, and then for the rest, right, the aircraft, you will start to see small little things that they do. For example, okay, by design they prevent water from trapping. Okay, if you look at the four things, right? Basically, you want to prevent electrolyte from actually being there. So a lot of things. Even for aircraft, right? The relative humidity inside there, right, is deliberately made low. Okay, that's why very uncomfortable. Okay,
Uncomfortable.
because not so comfortable. I mean, you feel dry, but if you make you feel comfortable, right, the aircraft will be very uncomfortable. You can actually, when you fly up to a high altitude, right, the skin there very cold. Your ice, next time you come down, you'll melt. Then you'll be trapped somewhere in the aircraft, right, that you do not see. You don't open up and see. So also part of the reason why people are doing things in a certain way. Okay. So this is the gist. All right. So now maybe I'll just try to go through the tutorial and then hopefully it'll be easy. Okay, so that's the kind of broad thing for revision and also exam. So what are the key things that you need to focus on? Okay, let's go back to tutorial proper. Okay, number one, briefly explain the difference between oxidation and reduction in a electrochemical reaction. Okay, this one I think I have a brief, I mentioned to you already. Okay, oxidation and reduction. Oxidation is basically anything that actually increase the valence state of the material. So just a very quick one, M, so let's say for example M, N plus, N, E, right? It throws away N number of electrons, become N plus. So this can be 1, and this will be 1. If it's 2, this will be 2. So in this case, you look at the number, right? Oxidize, this number will increase, alright? So this oxidation. So if you look at here, right? This is a process where I have a metal that becomes an ion. So this is also where corrosion is taking place. Okay, the reduction is the opposite, right? Mn.
Give away.
It takes electrons from the other side, whoever it is giving away, become Mn. So this is a reduction process. So this is at the cathode. This is at the anode. So anode is the oxidation process. Okay, so that's a briefly question number 1. Okay, can understand?
Yeah.
Yeah, good. Huh? Okay, question number. Ooh.
This one recorded, right?
Yeah. It's red light.
Green light.
Oh.
Sleep.
No, not that one.
Wow, sleep.
Okay, it's live recorded.
Boom, 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 boom.
Okay, so this one oxidation, this one reduction. Okay. Okay, now the second question is basically an application of the Nernst equation. Okay, in a standard condition, it's all 1 molar, 1 molar. The moment you start to see things like 0.6, all right, you know that it's no longer standard condition. You need to invoke that particular equation already. So that particular equation is a very simple idea. All right, in a standard condition, right, you always take the standard of let's say M minus the standard of N. Okay, the difference between the two electrodes will give you the so-called the value. So over here, you put your reduction minus your oxidation. So then you'll get a positive number. All right, reduction is on top, oxidation is below. So you take the delta something minus something, right? That will be a positive number. You do the reverse, you get a negative number. That's all. All right. So as long as they're consistent, then it is fine. All right. In this case, I have a concentration of copper and then lead. And in this case, right, the lead electrode is oxidized. All right, yielding a cell potential of this one. So this is oxidized, means a Pb somehow become Pb2 plus, right? And then the corresponding must be copper 2 plus becomes copper. Okay, so the one that is oxidized is this one. So when I write the equation, I'll write E, alright, I take the one that is being reduced, which is a copper, copper minus EPB will be equal to the standard condition, all right, of a copper minus standard condition of PB, all right, minus RT and F, okay, ln of PB and copper. All right, this is already given in a very simplistic sense, right? This is given as 0.507 volt. This one, right, you can find from the book value. Okay, you go to the table, you go to the EMF table. I think copper is 0.34, right, minus, this is actually a negative value, minus 0.126. So the delta will be
Plus.
U plus, okay, and then minus. R will be 8.314. The temperature will be 273 in Kelvin, right, plus 25 over N.
The R
Okay, what is N? I'll put it aside later. 96500, and then the ln of, okay, PB, which is the thing that they want you to find, right? PB 2 plus over this one, which is 0.6. So over here, the only unknown is this one, which is the thing that you need to find. What is this value? This N basically tells you in this reaction, right? When you do this simple reaction, how many electron transfer per reaction?
One.
So
Two.
two.
Sorry.
So this 2. That's all.
How many electrons transfer?
Yeah. I mean, for example, from copper to lead, right? There's 2 electron transfer from one side to actually complete the reduction process. Okay, and okay, so this 2.
Oh, that is 0.34.
Or let's say it's like
0.34.
5. Prof, let's say it's 5 plus, then the N will become 5.
Yes.
Okay.
But you never see 5 plus. I mean, 5 plus. Usually, you're talking about 1 or 2. Because 5 plus, you will have to throw away 5 electrons. Unlikely. You'll be in a situation where they want to share electrons already. That will be non-metals. So this one tend to be metals, right? Your metals are typically number will be 1, 2. Alright, so this is actually the application of Nernst equation. Okay, what happens if you guess it wrongly, for whatever reason, right? When you flip this number, if you flip this number, you flip this number, you flip on top and bottom, it will still be self-consistent. Okay. Yes, the table is actually you go back to your this one, right? Okay, this is actually the EMF table. So you go to the EMF table. Okay, this will be given over here. So standard electrode. Okay, I go and hunt for copper. Copper, where? 0.34 plus 0.34. Here, you can see.
Left, negative 0.126.
Okay, and then lead. Let me.
Minus 0.126.
Yeah, minus 0.126.
These are the zero conditions, right?
Yeah, this is the standard condition. Over here is the standard condition. Okay, when you're in the standard condition means 25 degrees, 1 molar, right? Then you don't have to do this calculation. The moment it deviates, right? So for example, this one is not 25 degrees, you go to let's say 100 degrees, okay, or 60 degrees. You are working in a hot environment. This is 60 degrees. You have to change because this is on the basis of this 25 degrees. So you will change this one, all right, and then you will be able to figure out. And also the molar condition is not 1, then you shift also. So it tells you, right, a situation, maybe under standard condition, the delta, okay, over here, if I take this number minus this number, what will be the value? 0.3.
166.
466.
466.
466, right? Under normal circumstances, right? the driving force, right, is only 0.466. Now because of this, you change the concentration gradient, right? Molar, right? Okay. The EMF becomes bigger. Yeah. So this one you can adjust the potential, alright, not by actually having the standard condition. You can actually change the electrolyte to change the so-called the voltage between anode and cathode. So this is what it means. So how you get 1.5 volt? Is it you have to find the right pair or you play around with this? So technically you have, right? Okay, so these are some of the tricks people use. Okay, so that will be okay. So for the following pair of alloys that are coupled with seawater, predate the possibility of galvanic corrosion. I think this should be possibility of galvanic corrosion rather than corrosion. Okay, let's be a little bit more specific. The question should write possibility of galvanic corrosion. Galvanic means you need two different materials to come together. So you look at aluminium and magnesium, right? So you just scan across here. Aluminium will be here. Okay, magnesium even lower. So you have relatively up and down. So based on this, right, the one that is down will be the one that corrodes. So for example, for some reason, right, you go and weld magnesium and then aluminum together and you put inside seawater, right? After a while, your magnesium will disappear. Okay, this is what it means.
Yeah.
Okay. Alright. So zinc and low carbon steel. Okay, same idea. You look at zinc. Okay, steel is on top. Zinc will be corroded. And in fact, zinc is something that what we people like to say the sacrificial anode. So if I have a structure that I want to protect, for example, a sheet, right? Okay. So this is a sheet on my this is iron, right? Okay. What I want to do is if I want to prevent the iron from corroding, right? I will stick a lot of these zinc blocks around. Okay. The zinc blocks become the anode. Iron becomes the cathode. Then iron will not corrode, zinc will corrode. As long as zinc is there, I know the ship will still be okay.
Oh, this one's the boat one.
Yeah. So one day, right, if you leave it for too long and nobody go and replace, right? Then okay, now the iron corrodes.
Sacrificial metal.
Yeah. So this is a sacrificial anode. So this is what people call SA, sacrificial anode. The one that you sacrifice to protect the bigger structure. So again, based on the corrosion idea. Yes. Yes. No. Yeah.
Hey, stop gaslighting.
Part D. Oh. Okay. So C, brass and Monel.
Raise hand immediately, pull down.
Okay, brass and Monel. So over here, you look at there's a square bracket. They don't write in so-called straight line. Actually, basically they are at the same level, which means, right, if you put them together, there's a very little driving force for corrosion. They may have corrosion by itself, but the galvanic corrosion with the EMF, right, is not quite there. So that's a basic design principle. If you are going to use in a moist environment or whatever, you always try to group the metals in the same category together. And in fact, you go to the notes, right? You look at Boeing, right? They also or Airbus, I forgot which one already. They do group their metals in a certain way over here. So they flip it. So the one that is not likely to corrode, they put bottom. I mean, it's up to them. But within the same group, right, they will try to use a material of the same group together. They will never want to cross group whenever they do the design. And this one is because of the reason that we talk about the galvanic series. Can? So this is their way of actually doing the galvanic series. Okay, make sense? Okay. Titanium and stainless steel. Titanium on top, stainless steel below. So when you look at here, titanium and stainless steel, right? Stainless steel will corrode. Okay, stainless steel is not stainless forever. Under circumstances, right, they will corrode. You put a stainless steel, right, and you put your gold inside it, right, your gold jewelry. After a while, you see the stainless steel corrode. Okay, because stainless steel is actually far below in terms of the galvanic series. This is what it means. And then cast iron and steel, they are pretty much in the same. I think close to the. It's slightly lower. Okay, cast iron will corrode. Okay, so very simple. So over here, from the galvanic series, side 3 metals that may be used to protect 304 stainless steel in active state. So we go for 304 in active state. So active and passive, right? You realize that active is far lower. Active, right, means the oxide has disappeared. Passive is still there. So you expect the active to be far lower in the series, right? Because the propensity for corrosion is much higher. So if you have something at the active state, what are the things that can actually protect it? So if this one to be the cathode, then you have to use everything below as the anode. So any of this material, anything below will be good. But I think I also want to come up with this part, right? When I say everything below, right, that will be what a chemistry teacher would say. But as an engineer, I need to look at it, some of the issue. Okay, for example, if I'm doing a protection of this, right, in a sea environment, right, I'll never want to use cadmium. Yeah, cadmium. So this one, because this is actually poisonous. You do not want to, well, you want to protect. You also don't want to create more damage to the legal system. So in a certain sense, right, for that reason, right, zinc will be a very good case. Magnesium, okay. Aluminium, probably okay. Cadmium, those are toxic metals. Although you can protect, try not to use it. Okay, so from the engineer's perspective, it's not just about what works, and then you have to look at the whole picture. The safety, sustainability, and the whole, what is the best choice? Of course, the lowest dollar also. Okay. If you have a choice, I try not to use things from Russia for now. That will be very expensive. What? Cadmium tends to be a very toxic. Yeah, cadmium over here, this, at least from here, this list, right, cadmium is the one that is toxic. Yeah, cadmium I will not use. Aluminium, I think quite okay. We use it in our everyday life, our pots and pans. Alright. Even for example, some of the pill that we eat, right, the tablets of antacid, I'm not too sure there's aluminium also. So I think we are quite okay. Alright?
But why the fuck would you use nickel cadmium?
What?
Sorry. No, I was asking why they use nickel cadmium battery when the electronegativity like quite close like that.
Nickel cadmium.
Yeah.
Nickel, cadmium is here. Nickel is on top.
Oh, passive nickel, man. I don't know.
Yeah, I think you want to look at this, right? You might want to go to your EMS series, because when you do this, right, you are dealing a little bit more closer to pure material.
Oh, okay.
Nickel, where? Can find? -2, cadmium -4. It's about 2 volts. 0.2 volts. You probably have to adjust the electrolyte concentration to actually give you that boost in the number. Okay. Okay, describe the phenomenon of passivity. I think I've actually mentioned just now in the overview. Passivity is basically adherent oxide. Okay, stainless steel oxide is very, very stable and it stays there. It doesn't come off easily. You try to scratch it, it stays there. Okay, unfortunately for one class of material, right, we always have a problem with iron, right? Rust, right? But the iron rust is not stable. Okay, when you have a rusty thing, right, you go and use a hand to touch, right? Your hand becomes brown color, right?
Yes.
Oxide, not stable. So it actually easily removed, which means every time it oxidizes, right, it will also come off. It's not so adherent, it's not protective. you allow more and more attack. It doesn't form that protective oxide, and that's why iron is not stainless. Okay, when you try to make the iron more corrosion resistant, right, you go and dump in things that can form the passive oxide, which is chromium and nickel. Okay, so name 2 common types of aluminum alloy that can do this. I would say stainless steel and aluminum. Aluminum forms a very stable oxide, aluminum oxide, which is a ceramic. Yeah, alloys, aluminum alloys, they will have their oxide naturally. The moment you actually take it out, right, after a while you have oxide on
There
top.
won't be any
Hmm?
when you touch those things, there won't be
Yeah, I think it will be very stable. Alright, you do not expect it to your hand to be dirty. Well,
Iron
of course,
is
those are
rust.
white lah. I mean, a bit transparent. You can't really see as much. Unfortunately, iron is a little bit brightly colored, brown, not so nice. Every time you touch it, your hand will all brownish. The oxide is not stable. It comes off.
So iron is like
Yeah, it's always on the active. It doesn't form a passive layer. So every time the oxide right, peel off, you scratch it right, you just easily remove and expose new surface, and things will just continue and continue.
Oh.
Okay, number 6 is why chromium in stainless steel make them more corrosion resistant. This one explained already. Yeah. Okay, for each form of corrosion, other than uniform, do the following, and this is something that I want you to know well. So, for example, what is crevice corrosion? What is filiform corrosion? Okay, what is fretting corrosion? So over here there are 11 types, right? Yeah.
Just remember like
The 11 kind of a corrosion, how does it look like? And how do you actually prevent some of those things from happening? Okay, cite 3 measures that may be taken to actually prevent it. So knowing them, able to actually see something and then you know what it is, right? And then recommend a course of action. I think it's important, at least. Course of action, like for example, you have a filiform corrosion, alright, which is under the under the paint, right? So most like a crevice corrosion. That thing is caused by concentration cell inside there. Okay, some similar to crevice, and this one is actually caused by a break in the membrane. So probably you have to do a little bit on the QC on your paint. Make sure that it's not as permeable to prevent the water from ingressing into the paint. So inspection around those areas might be important. Alright, so the quality of the paint will be one big. So some paints are expensive, some paints are cheap. There's a reason for that. Okay. Explain why cold metals are more susceptible. In general, things that is more cold work, right? They has more defects. More defects means if you use a very more layman terms, right? It will be energetically more unfavorable. They will more be likely to be the one that actually undergo certain reaction. So, for example, if I have a lot of dislocation and whatever, right? Okay, maybe I use a very simple idea. In some of the picture when we have grains and things, or maybe I can pull up a picture first. Okay, sorry. Remember, if this is a structure and these are all the grains.
Hey, Rick. It's okay. It's fine.
This is a stress coefficient. No. These are normal grains, right?
And
how do we actually see the grains? And you know what? How people prepare and how these grains come out in the laboratory. Okay. I'm doing this. I have somebody who is doing this work. Okay. Maybe I share with you.
Report. It's a report.
Not capstone. No lah. B minus.
Oh shit!
Average rate from our test.
We talking about the lab. We talking about the grade. The A star labs, bro.
Average rate is given as.
Is it really?
I think it's hitting.
I know. I came from A star.
Really?
Yeah.
He came for A star means his grades all A star. What?
Okay, I was actually sent by
Sent by the
web
lizards.
man. I was sent to do my PhD by NSTP. Somehow, after I studying halfway, right, they sent me another letter. Oh, the company that you are now bonded to is called A star.
Wow.
What's NSD?
So those are the days, so I'm that old.
You look like 30.
Okay, over here. So maybe this example, this is a work that the one that they pay us quite a bit of money to do. So this one, you see all the grains, right? How do we actually see the grains?
The
over
dot,
here?
the boundary
Yeah, the
line.
grain boundaries. Actually, what we do is we take a sample, we go to the lab, we polish and grind until it's mirror finish. We polish, it looks like a mirror. But how come the grains will appear? Actually, we put inside the acid. The acid will preferentially only attack the grain boundaries. Why? Because that is the unstable side. Remember, everything in the bulk, I'm very happy. Grain boundary, not so happy, easier to attack and remove. That's how we decorate the grains, and that's how we see the grains. In a very simplistic sum. Okay, so in general, any cold work material with a lot of defects will always be more susceptible to attack
Because for
compared
more
to
boundary
a new
lines.
one. Okay, so this is how it comes. And this, when you see the microstructure of all this thing, it's a very simple idea of corrosion you use to have advantage to do certain things. And in this case, right, we use it to study metals. Okay?
So as long as he has cold work, make a lot of defense, then it will be.
Compared to one that no cold work, right? You put together as a cathode anode, right? The cold one will become the anode. Yeah, this location there. Actually, when you do the part, right? And how do we actually figure out how much this location inside? We polish again, we etch it, and then you start to realize that, the dislocation is like a line, and then it will terminate somewhere at the end, right? You start to see pits.
That's not precipitate, man.
No, this is not precipitate. No, the one that actually goes to the end, then you start to see maybe a triangle shape. Basically, that's where the dislocation ends. And when you look at the dislocation, remember, the line, there will be a whole column of atom that is not satisfied, right? The topmost one, preferential. If I want to attack everybody, right? This is the part where I look down, right, from the edge dislocation. Okay, remember? I will attack here. This is the non-favorable side. So anything that is non-bulk, highly coordinated will always be preferentially attacked. Yeah. Yeah. So this one, imagine this is at the surface, right? This will be the one that's being attacked.
Coherent will
when
attack,
people figure out, right, tells you, oh, I have this amount of this location inside. How do they do? They actually etch a thing and just count how many of these pits that suddenly appear. And these are attributed to this location, and they give you an idea. This is a dislocation density.
Prof, so between coherent and incoherent precipitate, coherent the more likely one to be attacked in this case?
Coherent in a sense less likely because they are all coordinated. Incoherent, there's some bonds are not connected. Coherent means all the bonds go all the way through. There's no boundary, there's no unsatisfied bonds. Yes.
So just talk about grain
Basically,
boundary.
Okay. When I try to tell you, when I learn materials, I always imagine myself as an atom. If I'm at this location at this particular point, right? I have one neighbor shot.
Then they will attack you.
Yeah. I'll gonna whack
Living a
much
food rule.
easier. Make sense? I try to use a simple analogy. Yeah. Okay. Whatever you say, but don't write work in the group inside the exam or whatever. I will not accept it.
The guy that take video no, we take selfie bro, that's the best.
No. When you have a dislocation, just imagine, I have a box of this. Just imagine a measuring box. I have this location here. Eventually, if this is the surface, right, it has to terminate somewhere, right? If I have this location here, if I cut here, if I look here, I have something that's trying to go here. This is actually at the terminal. So if I polish the surface, it will be mirror shine. But actually over here locally, right, I know that one of the atoms, right, this particular atom has one less connection. So when I put inside the exit, right, alright, I sample across. Everybody are all well coordinated at this point, not coordinated, I'll adapt here.
The ones.
I mean,
But you mentioned, do you need to say that you need to polish?
oh, this one, how we do it is because we polish, we actually have a flat surface, so easier to see them. Yeah, mirror finish. Remove all the scratches so that when you see, right, it's really just a grain. When you have, if it's not shiny, right, you have a lot of lines, you don't even know whether it's the grain or whatever. So we always polish to mirror. Okay.
Which one is the grey?
Okay.
Which one are there?
Okay. Briefly explain. For a small anode to cathode area ratio, the corrosion will be higher or lower for this. Okay, this one is just a hypothetical example. So, hypothetical, I'm talking about governing corrosion. Just imagine you are in a situation where you have two pieces of, let's say, electrode, this anode, and this is a cathode. And then this is something here. Okay. So this is almost like a governing corrosion, right? If you have one can of paint, only one can of paint, you paint anode or you paint cathode? You paint cathode or anode? This is the one that will corrode. Anode is the one corrode. No. If you want to actually reduce the corrosion, right? You can paint it, right? Then insulating.
That's prevent it from touching the electrolyte.
Yeah. So will you paint the anode or you will paint the cathode?
Anode.
I think you paint the anode.
The more negative one, the more negative one.
Okay. Okay. I have anode, I have cathode, I have this one, right? It will be immersed in the liquid. So let's say you only have money enough to paint cathode or paint the cathode or anode, right? One piece only. You just have enough paint to paint cathode or anode. Which one will you paint?
The one giving the electron.
It gives out the electron.
The one that gives out the electron.
The one that gives out the electron. So the anode, right? You
Yes.
paint the anode. Okay. Yeah, good. So you paint here.
I don't know. I just
Nothing will happen,
common
right?
sense proof.
The moment you paint, nothing will come. This is the ideal world. But what happens if there's a scratch?
Start leaking out
You have a scratch, okay?
very small.
So the anode, right? The part that is being exposed, right, is seeing a huge demand of a cathode over here, right? We want to actually drive a lot of the current. This will actually have a very high current density. So this one will corrode very aggressively.
Wait, say again?
Okay? If I have a small little cut over here on a pane at the anode, the demand for electrons over here, right, I demand a lot. Yeah, the driving force, I demand a lot of electrons because the surface area is very big. Okay? This one have to provide. So over here, the corrosion will be very aggressive and very locally, very fast. Okay? If I coat the other side, cathode, right, who is demanding, right, all trapped. If I scratch, right, there's only one small little area that's demanding over the whole surface area.
Oh. You suck the thing out very fast like a
So
straw.
your cathode, right, you paint the cathode,
Like,
the anode will not have a very localized attack. If it has a scratch, right?
Slurp.
It will be more uniform. Does it make sense? Yeah. So last year, a lot of people get confused when I say this, right? Okay, maybe I use an analogy. Okay, anode is the good guy, cathode is the bad guy. And you have a fence, right? You want to fence up the good guy or you want to fence up the bad guy?
Depends on the bad guy.
Huh? Fence up the good guy. If the fence break, right, that one good guy standing at the open area is going to face a lot of bad guys. You go and fence up all the bad guys. The break, right, there's only one bad guy with many good guys. In general, all the good guys will feel less threatened, right?
Only one person can come
No,
out
I
from
mean,
the
that's
fence
not
at
personal.
once.
Typically, when you have pain, right, sometimes you will actually get scratches or whatever. And that's a relative. The pain will not be there. Yeah, and that's why we have certain issues. Does it make sense?
Bentix,
Up to you. I mean, for your thinking, I mean, I just try to tell you the ratio sometimes play a part when you try to do the protection. It's more for your consideration. Alright, the demand of electrons and the other one. Okay? Yeah, current. The demand for electrons is high. Because the surface area over here is I want more. Yeah, and this can be contributed only by a very small localized area. So I satisfy them through that. This one will be a very high localized attack. And if this is, for example, is let's say a vessel with a certain thickness, right? If a localized attack, right? It's not so good. You always prefer a uniform attack wherever possible. Okay, so that one is just an analogy. The bad guy, whatever, it's more for you to actually try to think through what it means. Okay, but please don't write bad guy, good guy. I will not accept it. I will give you 0. Okay. All right, and then last one. Describe 2 techniques I use for galvanic protection. Okay, galvanic protection. One of them, I think you all know already. If you are given a thing, right, for galvanic protection, of course that's by design. You do something, but if there is that, there's one way that you will do is your sacrificial anode. You use something to be the anode, so the one that you want to protect is the cathode. So this one, you always have an issue of you need to replace, right? But this is something that is also very good, right? If you know the population, right? You can bury something there. For example, all the underground pipes, right? They just don't lay the pipes on beside it, right? I mean, we lay the pipes, right? Cast iron or whatever. They also put something beside, so the cast iron don't go. And after a while, right? Instead of replacing the pipe underground, they replace the sacrificial anode. Yeah, must be cheap. And then it must last long. And the other way that people have done, right, if you look at here, I have an anode, I have a cathode, and the whole idea is this one will be the one that provides the electron to the cathode. So this one will be, actually, to protect this, we try to make sure that this will not be the anode, right? So this will be the sacrificial this. So is this the only way that you can actually prevent this from corroding? Using a material. Actually, another way of actually doing things is, for example, some of the big structures, what they have done is they don't do this. They create a power supply to actually drive current here. So they use basically electrical power to actually generate, to create a current, so that it flows this way. So this will be the cathode, over here will be an inert electrode. Okay, this one will not need replacing, but you need to actually turn the power on. So this technique is called impressed current. So you're actually pumping current over here to protect the structure. So for example, you have a structure that you want to actually protect. you can actually hook it to
Because
the mains
it's electronegativity,
without
so you give it an electron.
using a material. The idea is I try to prevent this thing from being the anode.
Prof, are all the processes reversible?
All the process, are they reversible?
Yeah, if you put a current through on the other side.
You put the current this way.
Yeah, if you input a current, is it reversible for all?
You do this way, then this one will corrode. You are actually extracting this out.
So then both sides.
So you have to pump current into, so that the circuit will be flowing this way. Okay? So the two methods, sacrificial anode and compressed current.
What is battery charging?
Okay? So compressed current, you do not have a consumable of the anode that has been replaced. You use something that's inert. Inert means it just become an electrode to actually fulfill the requirement of the electrical circuit. The electromotive force or whatever that drives the current is through power generation. Basically a device to pump current inside. What?
Impress current.
Impress.
Impress
Yeah.
So it's basically it's an external electrical source to provide current.
Correct. So this thing is okay if you have a civil infrastructure, like for example in Singapore or whatever, right? You can turn on the power. But you have a pipeline, right, that goes through Siberia, whatever, you cannot find plug. Right? Maybe it's easier to actually bury something there, can last for a couple of years, then every few years you go there and dig up that one. So again, for this thing to work, you need to have the power source. The other one, you don't have the power source issue, you just let the material deal with it, but that one, it will be consumed, you just have to replace it at the fixed duration. Okay? Yeah, the other one is a power source to drive the current. The other one is materials, the natural tendency, one want to give electrons more than the other to create the current. You don't provide if you provide the power source, that one will be always on the cathode, you will not corrode. If you do not turn on the thing, right, basically you will have a localized corrosion. It will be a localized within that itself, you have a cathode anode. This one you force it to be the cathode. Okay? Okay? Okay, that's all I have in terms of the corrosion. All good, right?
Results.
Okay. Okay, the results I tried to do a lot of things, right, but I still can't. There are quite a number of fail, but then when I look at net, right, you look at the assignment and things, right, it kind of brings you up. I have a very big range.
As all
I have
things
people
should
who
be.
got almost 4 marks, I have people who get 2.
If I balance means I pass.
I kind of struggle. I think the range is very big. So when I try to add up to the your assignment tend to do a little bit better. Then on average, it kind of helps you to pull up.
Can bring the
Okay.
weightage down for the
Wow.
Okay.
Assignment put 90%.
Yeah, assignment for 30%.
Okay. Exam is 30%. Do your exam well, then everything will be fine.
Okay, if I don't have any percentage to start
Assignment
with,
2, I will give it 6 to 9. Still try to do something about it. Okay. So this one, some of you really, some of the questions you leave it there. You really leave me with no choice. Sorry, Okay. Don't be disappointed. Whatever is a learning. I already post the answer online, so you just actually check. Anything just come to me. E-rate.
Anchong?
Yeah.
D1.
Oh, good.
Prof, it's out of how many? How much?
25.
25.
Ryan Chan.
Pass 18.5. Okay.
Yo Kun. Okay. C2. And
25.
Herman. Okay, don't worry, your Simon will pull you up. Xiak Peng. Jaden. Jaden Lee. Javier Low. Ahmad Sufan. Suyan.
Yeah.
Oh, it's a miracle.
12.5.
It's a miracle. What the What? Ay, Eric, lama. Nanti kau exam ni, mak. What the hell? I think I wrote a essay on it. Oh, really? Look at bro, nothing essay, man. You ever see what? You ever see first? I see 5%. I see before. I'll take it. I'll take it.
1% bro. 1.1%. Is it? 1.1%. Oh, 25.
Okay, for those of you who are not done well, not to worry. Okay, assignment will pull you up. There's still exam. For those of you who need help during this period, right? After you clear your first two or whatever exam, you need extra lessons, please feel free to contact me. Okay, my job is to make sure that you learn. It's not about just conducting the class.
Miracles happen.
Because from top to bottom, right, we still have a liquid and then solid, right? It's a range of where the
That's not the one you expected, right? Because I seriously expected that. Really expected.
0. But this case, right, you have a full range, right? You still have one. You have liquid. No, it's a range.
How much do you get, sir?
for the